To understand what the term minute of angle means, we first look at the circle. Webster defines a circle as a closed plane curve, every point of which is equidistant from a fixed point within the circle. There are 360 degrees in a circle. By definition, there are 60 minutes of arc or angle in 1 degree. 360 degrees multiplied by 60 equals 21,600 minutes of angle in a complete circle. The circumference of a circle equals 2 pi r, where r equals the radius of the circle and pi equals 3.1416. For any radius or range, 1 minute equals 0.0002908 r. If r equals 100 yards, which is 3,600 inches, 1 minute at 100 yards is 0.0002908 times 3,600, or 1.047 inches. 1 minute of angle covers or subtends a distance of 1.047 inches at 100 yards, or 5.235 inches at 500 yards, or 10.47 inches at 1,000 yards. For practical purposes, 1 minute of angle at 100 yards is rounded off to 1 inch. This value is close enough and easier to calculate for range work. At extreme long ranges, the 1.047 inches value will give more accurate results. Suppose you have your rifle zeroed for 100 yards. You now want to engage a target at 450 yards. Your dope data sheet gives you an elevation of 9.25 minute of angle at 450 yards. We know that 450 yards, 1 minute of angle equals 4.5 inches. So this tells us that you need to aim 41.6 inches, or 9.25 times 4.5, higher than your 100 yard zero point in order to hit the center of a target at 450 yards. If your scope has a quarter minute adjustment, you would need to dial in 37 clicks, or 4 times 9.25, for a 450 yard target. Some scopes have 1 minute or half minute adjustments. Others have more precise adjustments of 1/8 minute clicks. Quarter minute adjustments are precise without the tedious setting of 1/8 minute clicks. Half or 1 minute adjustments are too gross for precision accuracy. If you think in minutes rather than inches, adjustments can be made easily. For instance, suppose out at 800 yards you are off from center about 8 inches. This is 1 minute at 800 yards. Make a 1 minute adjustment to your elevation to be centered on the target. The wind drift is given in inches for a 1 mile per hour full value wind rather than minutes of angle on the dope data sheet. This is to allow for more precise measurements in the field. You'll need to calculate the minutes for your windage setting once the velocity, direction, and range have been determined. I use 10 mile per hour measurements and write in the minute of angle to adjust for a 10 mile per hour full value wind. Let's say my range is 300 yards and the wind is at 5 miles per hour full value wind. The minute of angle for a 10 mile per hour wind is 3.5. Just take it, divide 3.5 in half. The minute of angle adjustment for a 5 mile per hour full value wind will be 1.2 minute of angle, either left or right. Internal ballistics, the science of projectile motion within the rifle. External ballistics, the science of the bullet in flight. Terminal ballistics, the science of the motion and action of the bullet from the instant of initial impact until it stops. Everything that happens within the rifle, from the instant the primer is ignited until the bullet leaves the muzzle of the barrel, is important in terms of repeatability. Some components of internal ballistics: primer, powder, pressure, cartridge, barrel rifling and vibration, recoil, bullet, action, chamber dimensions, and other mechanical properties. The science of terminal ballistics involves everything that happens from the moment the bullet impacts the target until it comes to a stop. When the target is living tissue, terminal ballistics is also referred to as wound ballistics. Once the bullet leaves the muzzle, until the time it hits the target, its path is influenced by two external forces: gravity and the flow of air around the bullet. A solid understanding of external ballistics is imperative for long-range shooting. Gravity is a constant force that causes acceleration of a falling object at a rate of 32 feet per second squared. If there were no gravitational pull on the bullet, it would travel in a straight line. This can be called the line of departure. Gravity gives the bullet's trajectory its curved shape. The longer the bullet is in flight, the faster its falling velocity. The line of sight is a straight line from the sight to the target. This line is above the barrel or bore line. Bullet drop is the vertical distance between the bore line and the bullet path below it. The bullet crosses the line of sight twice. The second intersection with the line of sight is the 0 point. If you raise the angle of departure or increase the elevation, the bullet will travel further and hit high. If the elevation is decreased, the angle of departure is less, so the bullet does not travel as far and will hit low. Any gun that is sighted in on a level range will shoot high if fired either upward or downward. The force of gravity works perpendicular to the horizontal. When a bullet is fired at any angle, its horizontal distance is less, so it spends less time being affected by gravitational forces. See the section on dealing with angles. At close ranges or angles below 15 degrees, the bullet drop distance changes very little. However, at long ranges and very steep angles, the change in point of impact is significant. The second factor that influences the bullet in flight is air resistance, also referred to as drag. Drag works in opposition to velocity. The higher velocity of an object, the higher the resistance, which means more drag. Air density is affected by temperature, barometric pressure, altitude, and humidity. If the air density is high, then drag is increased. Low air density results in less drag. Air density increases as temperature increases. As temperature increases, point of impact rises. Air density decreases at higher elevations. Therefore, drag is less. The point of impact will rise with increasing elevation. As a rule, slight corrections should be made with every 1,000 feet of change in altitude. Obviously, if you have sighted your rifle at a lower altitude, then go to a high altitude, your impact will be significantly different at longer ranges, a fact very prevalent in the mountains of Afghanistan. Barometric pressure is a measure of air density. The higher the altitude, the lower the barometric pressure. The barometric pressure published by the Weather Bureau has been adjusted for altitude, so it is not a true measure of the density of the air. Believe it or not, humid air is less dense than dry air at the same pressure and temperature. However, humidity has a minor effect on point of impact, and has only a slight effect even if going from one extreme to another, and only at very long ranges. Another force which causes drag on the bullet is the speed of sound. Sound travels at 1,120.27 feet per second standard air density, 0.0751 pounds per foot cubed. When a bullet travels faster than the speed of sound, shock waves form around the bullet. The bullet must push these shock waves and move the air along the surface of the wavefront. This causes drag on the bullet, slowing it down. A second shock wave occurs behind the bullet as air rushes in to fill the void left behind as the traveling bullet pushes the air aside. Ballistic coefficient of a bullet, or C, is equal to the drag deceleration of the standard bullet divided by the drag deceleration of the actual bullet. The ballistic coefficient for the standard bullet is defined by 1.000. Since the actual bullet usually slows down faster than the standard bullet, C is generally less than 1.0. The smaller the C value, the faster the bullet slows down. The science of external ballistics is complex, with many factors influencing the trajectory of a bullet all at the same time. The serious long-range shooter should consider an in-depth study of this science to achieve accuracy. The higher the ballistic coefficient, the better it retains velocity. It resists wind better. It has a flatter trajectory, meaning it will take less time to travel to the target, giving gravity, air density, and humidity less time to affect the bullet. You can find ballistic information in books, software, even online these days. This book allows you to look up ballistic coefficient from 0.09 to 0.7, muzzle velocity from 1,000 to 4,000 feet per second. Determine the amount of drift and drop for a given bullet. What you're looking for is a ballistic coefficient of at least 0.4. Ideally, you want 0.5 or 0.6. This will increase the bullet's ability to buck wind drift and retain velocity. Now let's compare two bullets and see if we can pick the better of the two based on its ballistic coefficient. We're going to compare the 220 Swift and the 22 250 Ackley. In the 220 Swift, we're going to shoot a 50 grain bullet. Keep in mind this data is based on a 10 mile per hour full value wind. It has a ballistic coefficient of 0.24, a muzzle velocity of 3,900 feet per second. Its drift at 400 yards is 17.4 inches. Its drift at 800 yards is 96 inches. Its drop at 400 yards is 14.4 inches. Its drop at 800 yards will be 156.2 inches. Now let's look at the 22 250 Ackley. We're going to shoot a 70 grain bullet with a ballistic coefficient of 0.41. It has a muzzle velocity of 3,600 feet per second. Its drift at 400 yards will be 10.1 inches. Its drift at 800 yards will be 48.3 inches. Its drop at 400 yards will be 13.3 inches. Its drop at 800 yards will be 109.5 inches. Which bullet is more efficient? Obviously, the 22 250 Ackley would be a better choice for long-range shooting. Many companies put out good data books for the precision shooter. They contain tactical considerations for the tactical shooter, range cards, and dope data sheets. You just have to look for what works best for you. Whenever you shoot, on the range or in the field, take a notebook and record certain data. What to record? Number of shots fired. Distances. Windage and elevation that was dialed in. Something else you should note, that when you're shooting in colder temperatures, the air is denser, and the more elevation is going to be required. Elevation will play a part in minute of angle changes as the air is thinner and the bullet will have less drop. These will grow into information we know, i.e. when known at this range and wind speed, it takes this minute of angle adjustment at this angle for this wind speed for an accurate shot. When I go to the field or the range to shoot, I usually just bring a Rainwright notebook and pen. They can be written on when they're wet, they come with a nice pen, and the pages have graph paper printed on them that work well for range cards. The length of a football field is 100 yards instead of meters, but it is a unit of measure most of you are familiar with. Estimate the number of football fields between you and the target for ranges up to 500 meters. Multiply the number of fields by 100 to determine the range in meters. For ranges between 500 and 1,000 meters, pick a point halfway between you and the target. Determine the number of football fields, multiply by 100, and then double the amount to find the range to the target. It should be noted, after 300 yards, the average human being loses the ability to judge range accurately. This is when you can switch to the halfway point technique. Pick a point halfway between you and the target. Get its range and multiply by 2. If the range is at 150 yards to the halfway point, 150 times 2 equals 300 yards. A good laser rangefinder will give you very accurate readings. However, you need to weigh bulk versus accuracy. You might want to throw a set in your bag. Some are both binos and rangefinders. The paper strip method is useful when determining distances 1,000 yards plus. When using this method, you place the edge of a strip of paper on the map and make sure it's long enough to reach between the 2 points. Then you pencil in tick marks on the paper at your position and another at the distant location. You place the paper on the map's bar scale located at the bottom of the map. Line it up with the 0 on the scale, then you read it to the right to the second mark and note the responding distance represented between the two marks. You can order military topographical maps on the Winchester Firearms website for about $20. They come laminated and have elevation marks on the map. You can also use a range card to quickly determine ranges throughout the target area. Once a target is seen, you determine where it is located on the card and then read the proper range to the target. I prefer to figure range in meters, so I multiply the target size by 25.4 and then divide by the mil settings in the scope, and this will give me my target range in meters. I prefer binos with a mil-dot reticle to conduct hasty scans. They should be at most 7 power with a 50mm objective lens and an interpupillary scale located on the hinge. You should adjust the binocular until one sharp circle appears while looking through them. After adjusting the binocular's interpupillary distance, that's the distance between the person's pupils, you should make a mental note of the reading on this scale for future reference. The eyepieces should also be adjustable. You can adjust one eyepiece at a time by turning the eyepiece with one hand while placing the palm of the other hand over the objective lens of the other monocular. While keeping both eyes open, you adjust the eyepiece until you can see a crisp, clear view. After one eyepiece is adjusted, you repeat the procedure with the remaining eyepiece. You should also make a mental note of the diopter scale reading on both eyepieces for future reference. One side of the binocular should have a laminated reticle pattern that consists of a vertical and horizontal mil scale that is graduated in 10 mil increments. You can use the binoculars for observing target areas, observing target movement and positions, improving low light level viewing, and estimating range. The mil-dot reticle is the standard in tactical rifle scopes and what I use. The mil scale can be used just like a ruler to measure the height of a target. If the actual size of the target is known, then the range can be calculated using a simple formula. In these examples, I'll be using a modified mil-dot reticle. One difference from a standard mil-dot reticle is that a fifth dot takes the place of the broad post at the edge of the field of view. This reticle is a wire, 1/4 mil dots spaced 1 milliradian apart. There are 5 mils between the center crosshairs and the center of the outside dot. In this reticle, the dots are actually more oval than round. The length of the dot is 0.25 mil. Make sure when you purchase your scope, you know which type of mil dots you are purchasing. A milliradian is an angular unit of measure. 1 milliradian equals 1 yard at 1,000 yards and 1 meter at 1,000 meters. Review minute of angle. If you know the height of the target in yards, multiply it by 1,000 and divide it by the mil dot size of the target to get the range. I prefer to work in meters coming from the military side. For precision work, mil readings need to be accurate to the 10th of a mil. U.S. Marine Corps standards measures to the 8th mil based on the size of the mil dot, then converts to tenths. The mil dot reading for this target appears to be 1.3. Since we know the target is 30 inches high, 0.833 yards, we can enter this information into the formula. The actual range is 650 yards, so we came up a little short. However, at this range we are only 2 inches low, close enough. The horizontal mil dots can be used for hold-off in wind conditions or as leads for moving targets. The vertical mil dots can be used for elevation holdover or under when there isn't time to make an adjustment to the elevation. This may come in handy if the first shot misses a target and a correction needs to be made before the target gains cover. In order to use the mil dots for hold-off, you need to convert mil dot distance to minute of angle. This is where some confusion comes in. The reticle used in these examples uses the U.S. Marine Corps standard of 1 mil equals exactly 3.438 minute of angle. The standard used by the Army is 3.6. Many people use 3.5 since it is in between the two. Suppose your rifle is zeroed for 100 yards and you have set your elevation for a target at 600 yards, which you have just hit. Suddenly a target pops up at 400 yards. You do not have time to readjust the elevation setting to engage the new target. Since there is 7.75 minute of angle difference in elevation between 600 and 400 yards, you need to hold under 2.25 mils. 7.75 divided by 3.3438 to hit the closer target. Using the bracketing method, you assume that the target is no more than X meters, but no less than Y meters away. An average of X and Y will be the estimate of the distance to the target. You can use known distance from two terrain features by estimating their distance and taking the average. In the field, perfect conditions rarely exist. Therefore, only one method of range estimation may not be enough for your specific target. Terrain with much dead space limits the accuracy of the 100-meter method. Poor visibility limits the use of the appearance of object method. However, by using a combination of the two or more methods to determine an unknown range, an experienced shooter should arrive at an estimated range close to the true range. This chart is an example of a quick reference for a 6-foot man at varying ranges. If your scope doesn't have the mil reticle, you can use the duplex scope to estimate range by using the distance from the crosshairs to the thick portion of the reticle. Set up a yardstick at 100 yards and see the sustension from the reticle to your post. Write this down. Mil.master has a slide rule that will give you the distance to your target with a great deal of accuracy, so there's no need to do all that math. Bracket your target, count the number of mil dots, look on the scale, line up the arrow, and it will give you the range. The most challenging aspect of long-range shooting is understanding the effects of wind on the path of the bullet. The effect the wind has on the path of a bullet depends on the velocity of the wind and the direction in which it blows. The velocity of the bullet is relative to the air in which it travels. For example, in a tailwind, the velocity of the bullet is slightly less relative to the moving air than it would be in still air. Less velocity means less drag and the bullet hits a little high. The opposite happens in a headwind. The velocity of the bullet relative to the moving air is slightly higher. More velocity means more drag and the bullet hits a little low. Headwinds and tailwinds of lower velocities and at short ranges do not produce much of a difference in bullet drop. They can have an important influence at longer ranges and if the wind is strong. Headwind has slightly more of an effect than tailwind. Crosswind has a strong effect on the horizontal path of the bullet. Crosswinds that are exactly at right angles to the shooter's line of sight are called full-value winds. Winds at 60 degrees from the right angle are called half-value winds. Half-value winds also have some components of head or tail winds. A gust of wind close to the muzzle will have more of an effect on the bullet path than further downrange. A gust downrange near the target will have little effect on the point of impact. When shooting in canyons or mountainous terrain, there can be vertical wind effect which lifts the bullet. On target ranges, wind flags help determine the wind conditions. In the field, other objects such as trees and dust are observed to establish the velocity and direction of the wind. There are also reliable wind meters which give the value of the wind at the shooting position. One way to determine the direction and velocity of the wind is by observing the angle of heat waves, or the mirage, seen through the scope. Heat waves are caused when hot air near the ground mixes with cooler air above. The bending of light as it passes through the different densities of air causes the mirage effect. The target will appear displaced for the same reason. The heat waves will bend in the direction that the wind is blowing. In lower velocity winds, the waves will be oblique to the vertical line. At around 12 miles per hour, the heat waves are horizontal. If a wind comes from the left, or 9 o'clock, the bullet will be displaced to the right of the target if no adjustment to the windage knob is made. Measured in inches, this is called wind drift. To hit the target, the bullet impact needs to be moved to the left. The windage knob on the scope is rotated to move the impact left. In this example, note, I use 10 mile per hour winds on my dope data sheet. However, for this illustration, I'll be using 1 mile per hour winds. This range card gives the wind drift in inches for a constant 1 mile per hour full value wind. The drift is stated in inches to determine a more precise final value than if the drift was in minutes. Once you have determined the velocity and direction of the wind, convert inches to minute of angle to get a windage setting. Suppose you have a 10 mile per hour full value wind at 630 yards. That's 3.2 inches times 10 equals 32 inches. Divide 32 inches by 6.3 inches to get 5.08 minutes. Adjust your windage dial 5 minutes in the correct direction and you should hit the target. There can be different wind conditions all down the range affecting the path of the bullet. The only way to really understand the wind is to spend time shooting in it. A quick example on how to use this chart. Let's say you have a target at 400 yards with an incline of 45 degrees. Your minute of angle will be 2.75. Anything below 20 degrees won't require a change in elevation. You would multiply your range by the corresponding cosine. At 400 yards with a 45 degree angle, you would multiply 400 by 0.7. Actual range is 280 yards. On your dope data sheet, you will record the caliber, the type of ammo, the bullet used, the incremental ranges you zeroed at, the minute of angle to compensate for the wind, and the cosine for the angles. Many companies put out good data books for the precision shooter. They contain tactical considerations for the tactical shooter, range cards, and dope data sheets. You just have to look for what works best for you. Whenever you shoot, on the range or in the field, take a notebook and record certain data. What to record? Number of shots fired. Distances. Windage and elevation that was dialed in. Something else you should note, that when you're shooting in colder temperatures, the air is denser, and the more elevation is going to be required. Elevation will play a part in minute of angle changes as the air is thinner and the bullet will have less drop. These will grow into information we know, i.e. when known at this range and wind speed, it takes this minute of angle adjustment at this angle for this wind speed for an accurate shot. When I go to the field or the range to shoot, I usually just bring a Rainwright notebook and pen. They can be written on when they're wet, they come with a nice pen, and the pages have graph paper printed on them that work well for range cards. What is a dope data sheet? Also known by some shooters as a range card. It is basically a list of known factors, placed somewhere on or near the rifle, to facilitate quick manipulation of the elevation and windage knobs to compensate for external ballistic factors. Here's a sample dope data sheet. Keep in mind these numbers aren't accurate. I just made the sheet to show what it should contain. The first column is your range that you zeroed at. Remember, you zeroed at varying ranges to note changes in bullet drop and windage settings. The second column is minutes to zero. In a 10 mile per hour wind, we have a 4-inch correction. That is the third column. From the fourth column, you get the number of minutes you have to dial into your scope to bring it back on target. Ballistic data for your dope data sheet can be taken from software. And from ballistics books, such as this one by Philip Manns. However, the most effective way to put together your dope data sheet is to use calibrations from firing on the range for your notes. Each rifle shoots differently depending on the shooter and the setup of the rifle. A quick example on how to use this chart. Let's say you have a target at 400 yards with an incline of 45 degrees. Your minute of angle will be 2.75. Anything below 20 degrees won't require a change in elevation. You would multiply your range by the corresponding cosine. At 400 yards with a 45 degree angle, you would multiply 400 by 0.7. Actual range is 280 yards. On your dope data sheet, you will record the caliber, the type of ammo, the bullet used, the incremental ranges you zeroed at, the minute of angle to compensate for the wind, and the cosine for the angles.